what we're going to do now is talk about a general rule that will allow you to kind of sidestep the necessity to go through this carbocation mechanism every single time to try to predict the product. So, after you do the mechanism enough, it kind of becomes second nature to just kind of do it in your head. But until you get to that point, there's a quick fix for trying to predict products from alkenes reacting with hydrogen halides. So there's actually a rule that's it gets a name, and it's called Markovnikov's rule. So Markovnikov's rule says a few things, and so we're just going to talk about formally what Markovnikov kind of tells you to do to kind of sidestep drawing out the mechanism for these types of reactions every time. So the way to think about Markovnikov's rule is we can think about it both from the terms of the electrophile and also in the terms of the nucleophile. So we're going to frame it from both perspectives just to kind of give you an idea of what's happening. So Markovnikov's rule, or Mark's rule, says that electrophiles are going to add to the carbon with the most number of hydrogens. So in this case, we could think of the hydrogen as both being a hydrogen and also being an electrophile. So it's kind of that same concept of having different relationships but being the same person that we talked about a couple of videos back, where this hydrogen from the HBr is definitely acting as an acid, but you could also frame it in terms of being an electrophile because it's being attacked by some electrons. So this hydrogen that we are playing around with, it's going to add to the carbon with the most number of hydrogens. So let's call this carbon on the bottom carbon 1 and this carbon on the top carbon 2. And let's try to quantitate how many hydrogens are on carbon 1 and carbon 2. So carbon 1 should have, at this point it should be like almost instantaneous that you should know that on carbon 1 we have 1 hydrogen right there. And it should be instantaneous that you should recognize that on carbon 2 there are 0 hydrogens. So now, going back to this rule that the electrophile, in this case, are our hydrogen, our H+, this electrophile is going to add to the carbon with the most number of hydrogens. And then in this case, that's going to be carbon number 1. So one way to say this is, okay, the electrophile is going to add to the carbon with the most number of hydrogens. So this pink hydrogen is going to be adding to carbon 1. And so that's all well and good, but we're kind of doing the same thing as going through a mechanism at this point. The other part of Markovnikov that kind of lets you sidestep the mechanism is that we can say that the nucleophile adds to the carbon with the most non-hydrogen substituents. So in this case, this is kind of just a complement to the first part of this Mark rule, which is that carbon 2 versus carbon 1, if you count the substituents on carbon 2 has 1, 2, 3 substituents, so that would be carbon 1. And then carbon 1 has 1, 2 substituents, not counting the hydrogen. So we're counting most non-hydrogen substituents. So in this case, if you have to put the nucleophile on carbon 1 versus carbon 2, we have to recognize that the nucleophile is our bromine. So our bromine minus is going to be our nucleophile. And so now we know, okay, carbon 2, that's going to be where we put our bromine. So Markovnikov's rule is very nice to kind of sidestep the mechanism if you're trying to get to the product very quickly. So notice I didn't have to draw any arrows, I didn't have to draw any charged intermediates or anything like that. I just, I have the starting material on the left, have the, reactant in the middle, and the product on the right. So A plus B equals C. So, Mark's rule is it's pretty good as a sidestep. It has its limitations, and we're going to find out those limitations in the next couple of little videos. And it doesn't have to always be the electrophile being H+ and the nucleophile being Br-. That's the beauty of Mark's rule, is that you can kind of have it be a very wide generic rule. It doesn't have to be H+ for electrophile, and it doesn't have to be Br- for nucleophile. So just keep that in mind. That'll make a little bit more sense later on.